Have you ever looked at a map and noticed how it doesn't do a particularly good job of showing you what the landscape really looks like? This is because maps have to summarize a lot of spatial information and fit it into a small space. For example, topographic maps have to show three-dimensional features of the landscape, yet do so on a two-dimensional sheet of paper. This requires users to work in 2 dimensions while simultaneously thinking in 3 dimensions. This is not an easy task for many people. To become proficient in interpreting topographic maps, we must use abstract spatial thinking skills. We hope this experience will help you to improve some of the skills associated with spatial thinking. Although the spatial thinking skills that you will learn and use here are specific to topographic maps, many courses and careers require people to think spatially. This experience will be of interest to anyone who wants to improve their spatial ability. These skills have been shown to contribute to success in science, technology, engineering, and math careers. This instructional module will cover these 4 major topics. Following instruction, you'll have an opportunity to apply some of the skills and knowledge you've learned by interacting with a topographic map. Although there are many types of maps, a topographical map is unique because it provides a graphical representation of the shape of the Earth's surface. It displays spatial information such as location, elevation, distance, and direction. Here's an example of a topographic map from the United States Geological Survey. The defining characteristic that makes any map a topographic map are the presence of contour lines. Contour lines are imaginary lines that connect points of equal elevation, and in doing so they form concentric circles. They are shown here in this example of a very steep mountainous landscape. Topographic maps show the shape of the landforms and elevations above sea level in either meters or feet by using these topographic lines. Most topographic maps are shown as if you're looking down on them from directly overhead. This is referred to as a plan view. Color is sometimes used as a visual aid to understanding relative differences in elevation. For example, different contour lines are given different colors in the example on the right. Note in the example on the left that as the elevation increases, the concentric circles become smaller. This is an important concept to remember. So as we move inland and the elevation begins to rise, eventually reaching the summits of Mauna Kea and Mauna Loa, those concentric circles are quite a bit smaller than the lower lying areas, which are encircled with larger concentric circles, indicating their elevation. Another way to understand how two-dimensional surfaces on a topographic map actually represent a three-dimensional object is by creating a cross-section. Note how each contour line from the plan view at the top is associated with a particular elevation using the scale in the cross-sectional view. Creating a cross-sectional profile indicates how elevation changes with horizontal distance. We can use contour lines to indicate elevation, otherwise known as altitude. Elevation or altitude is the height in feet or meters above sea level. Topographic maps use 2 types of contour lines. Index contours are bold lines with the elevation listed as shown at point A. Lines that do not have elevations listed are called intermediate contours. Topographic maps are labeled with a contour interval. The The contour interval is the difference in elevation from one contour to the next. You can use this value to calculate the elevation of an intermediate contour by counting from the nearest index contour. At any point along a contour line, the elevation is the same. So what would the elevation be for point B? 720 feet. What about point C? Point C has the same elevation because it's located on the same contour line as point B. Now try to determine the elevations at point D and E. Point D is 760 feet. E is 820 feet because it is 20 feet above the 800-foot index contour. Now we're going to turn to look at how to recognize landscape features based on the shape of contour lines. We'll look at two main categories. These are known as elevated features. We'll also look at features that are created by erosion, such as water, ice, or wind. At the end of this module, we'll practice creating different examples of these landscape features using topographic contour lines. Then we'll identify examples on a map. Let's begin by looking at the steepness of slopes. Examine the landscape illustration on the right and compare it to how it would appear in the topographic map on the left. You'll notice that gentle slopes have widely spaced contour lines. We'll use this same comparison strategy between topographic lines and example landscapes throughout this section. Steep slopes are the exact opposite of gentle slopes. They have closely spaced contour lines. It's often confusing when determining the difference between a hill and a mountain on a contour map. For our purposes, we define a hill as having rounded contour lines with a fairly dome-like summit. The contour lines are regularly spaced. And a hill is always a lower elevation than a mountain. Since mountains are higher in elevation than hills, they tend to have a more irregular shape to them. Notice here the contour lines are highly irregular. They're jagged. They also have much steeper slopes and can include other more complex features such as cliffs, valleys, plateaus, etc. Ridges are similar to hills and mountains, but their defining characteristic is that they're elongated. Imagine a hill or a mountain that's been stretched, forming a line of elevated terrain. Ridges can be found at low elevations and may connect hills, or at high elevations and may connect mountains. Think of the idea of a mountain chain. The next landscape feature that we'll examine is a feature that separates hills and mountains into individual features. A saddle is a low point that separates two high points. They could be two hills in a small ridge or two mountaintops in a much larger ridge. Study the landscape and topographic map profile carefully. Notice the characteristic saddle shape, as shown here, with a low elevation area separated by two high points. In this topographic profile example, this is a high point here and here. Where would the low point be? This is the low point of the saddle. When you have a ridge with multiple saddles in it, you have a ridge line. So here are our high points, and here are low points. These are the saddles. An image of a mesa is shown on the right. Mesas are essentially flat-top hills. The flat area on the top of the mesa can also be referred to as a plateau. The key defining feature of a mesa is that it is surrounded by very steep slopes, usually cliffs. You will notice the close spacing of topographic lines on the edges of the mesa. Buttes are very old mesas that have essentially worn away until all you have left is a very tall spire. It is also surrounded by cliffs, but has little or no remaining plateau. Valleys are typically created by water flowing down slope, usually in the form of a creek or a larger river. The valley is located here on the landscape view. Valleys are recognized by a characteristic topographic map pattern. This is the river here. Notice the V-shaped contour lines. These are characteristic of any river valley. Also notice that the V's point uphill. A spur is a combination of two features, a valley and a ridge. Spurs and valleys often occur in a repeating fashion. They're common features of ridges and mountains. This is the ridge, and it's been eroded by 3 river valleys in this example. Here, the uphill pointing V's indicate rivers. The spurs, the areas between the creeks, are generally lower angle, and they sport U-shaped topo lines. So V's pointing uphill indicate valleys, U's pointing downhill indicate spurs. Depressions or basins are areas that are below the average level of the landscape. These are locations where water tends to collect from rainfall or stream flow. In the maps that we will use, color will provide us an aid to determining relative elevation. Darker colors are associated with higher altitudes. Now we're going to visualize landscape features that we've identified using this imaginary 3D oblique view landscape. Note that color is used to show relative elevation. Green is the lowest elevation and white is the highest in this example. If you were standing at point A, would you be able to see point B? The correct response is no, because of the presence of this mountain here, which would block your view. Which route would you take if you wanted to take the easiest, lowest angle route to travel on foot from A to B? The route marked in red is easier, even though it is longer, because you travel on the lower angle slopes on the side of the mountain, as opposed to the black route, which is shorter but more strenuous climbing up and over the summit. North is shown in the upper left-hand corner of this map. Which of the views in the next slide would you have been looking north when standing at the saddle at point B? Which of the 3D views on the left has you looking north as if you're standing at point B? North is marked on the plan view two-dimensional map on the right. The correct answer is number 2. North is shown on that view. This is what the perspective would be from 2 dimensions. Number 1 has you facing south, and number 3 has you facing west. On the next slide, you'll be asked to rate the mental effort required to answer this question. Use your mouse to scroll down and click on the check mark that corresponds with the mental effort needed to answer this question. Once you've done that, click on the Submit button in the bottom right-hand corner, and then a Continue button will appear, and that'll allow you to advance to the next slide. We'll be using this mental effort rating after each question for the next few slides. Use this 2D version of our topographic map to identify as many of the landscape features as we've talked about. Once you've done that, press the next button to advance to a slide that will show all the landscape features but in 3 dimensions. Let's compare some of the sample landscapes that we identified in the previous 2D view of this map. We'll begin by looking at a ridge here, the summit of one mountain, the dual summit of a second mountain. We have ridges here that form a creek basin. The upward pointing V's are our clue. We also have a basin that forms a saddle into our dual summited mountain. We have a creek that drains here as well. We have ridges that form spurs here, the downward facing U's. We have a saddle here, here, and in this area right here. Basins are shown here, here, and in this area here. For our final exercise, we'll be comparing 3-dimensional shapes to their location and shape on a 2-dimensional map view. Have a look at the 2 photos. Where would they be located on this new map? The top photo corresponds to a ridge. The bottom photo corresponds to this mesa. Where would you find these 2 3D landscapes on our 2-dimensional map? The top photo corresponds with a depression or basin, shown here. And a snow-capped mountain is shown here. What 3-dimensional view corresponds with a similar feature on the map? The figure on the left corresponds with the valley as shown here on the map. Which direction does the valley flow? From the upslope or high elevation area to lower slopes? This is shown by the arrow, where the valley drains from the saddle down into the basin.